All right. Hi, everybody. Welcome. And we are today going to focus in on net ionic equations. And since I can't be there in class to offer you some support, do some entry task stuff today, I thought I'd just throw up a couple of practice questions with some of my support in video form so you can kind of get some help navigating these particular questions. All right? So we're going to focus in on question number 2, followed by question number 6, and then we'll finish off with question number 9. Just sort of a random sampling of the practice questions from the net ionic equations sheet. All right, you are going to want in front of you your solubility rules, your periodic tables, and so on. I put a little copy of the solubility rules here so that we have that in front of us as we navigate these questions. All right, so let's get started. So question number 2, we have aqueous solutions of barium chloride and sodium sulfate. All right, so I'm going to recommend just to help make sure that we have the correct starting point for each of these questions, going all the way back to square one, we have to write the correct formulas for barium chloride and sodium sulfate based on those rules we learned 2 months ago as we were learning to write the formulas for ionic compounds. So barium, so here's how I'm going to start this up. I'm going to write barium, Ba, which is the chemical symbol for barium, and we know that that's a 2+ ion, and we get that from our periodic table with the fact that barium is in the second column and chloride is Cl, and it's a -1. All right, now we'll go over here to sodium. Sodium is a +1 ion, so just get a little plus. And sulfate, that ATE ending tells us that's the polyatomic ion, SO4, and that gets a little -2 next to it. Okay, now taking the time to do this, particularly with our polyatomic ions and our net ionic equations, it's just going to help, and it's going to help us avoid problems, right? So let's go ahead and write our formula. So our molecular equation, Me, is going to be the way that we learned how to write equations from the get-go. So we're just going to go Ba, right? Now, because this is a +2 and chlorine is only a -1, right, we're going to have to indicate that we, in fact, have 2 chloride ions for every 1 barium, because we need 2 chlorines in order to make that a neutral compound, right? And this is told that it is an aqueous solution. We're going to also go ahead and indicate that with a little AQ, okay? And we're going to mix that with sodium sulfate, right? Now, sulfate's a -2 charge that polyatomic ion has. Because sodium ions are only a +1, we're going to need 2 sodium ions. So it's Na2, SO4, and also going to get indicated with an aqueous solution. All right. Now, here's where we start applying our understanding of various reaction types to predict what these products ought to be, right? But also to try to determine, is a reaction going to occur in the first place? And this being what looks like a double replacement reaction, right? We will use these solubility rules down here to make sure that at least one of our products is not going to also be an aqueous solution or stay in ion form, right? So if a precipitate forms, that means we're going to have an insoluble compound, that we would predict there will be a reaction. Or if water forms, HOH or H2O forms, we would also predict that there would be a reaction. If all of our products are aqueous or soluble, we would then say no reaction. All right. So essentially what happens, right, with our double replacement reactions is our 2 positive ions, sodium and barium, will swap partners, if you will. All right. So let's do a quick check. If I form sodium chloride on my other side, all right, so I'm going to write NaCl, right? Sodium's a +1, chloride's a -1, so they're already balanced there, so we don't need any additional subscripts. We're just going to check our chloride ion here. usually aqueous. All right, so the only time chlorine would be insoluble, or chlorides, excuse me, would be insoluble, are when they are paired with silver, mercury, or lead. And so since sodium is not an exception, we're going to indicate an AQ here. Right? And we're going to add to that our second compound that would form, which would be barium sulfate. So barium's a +2. Sulfate's a -2, which makes that easy. We don't need to have any additional subscripts. Okay? But let's go down and check. Sulfates here are usually aqueous. Okay? But we need to check whether barium is an exception. And it turns out right here it says barium is an exception, which means that when sulfates, which are usually aqueous, are with barium or strontium or mercury or lead-2, right, they are in fact not soluble. So we did form an insoluble product, which means there is a reaction. So we're going to go ahead and carry this forward. BaSO4. Now notice, of course, that little 4 right there, which is a part of that polyatomic ion, remains. We don't need any additional subscripts because it's a +2 and a -2, so one of each will go ahead and bounce each other out. But we have to do this last little part and indicate that that is in fact a solid that forms. And that's what indicates to us that there is in fact a reaction, and we will go ahead and proceed to balance this thing. And this is a pretty easy one to balance, right? We have 2 chlorines there, only 1 here, so let's just start with the 2 right there, which also gives us 2 sodiums on both sides. We got 1 barium, 1 sulfate on both sides, so that's balanced. All right? So that is all of topics 5.1 and 5.2 combined. All right? Now, moving forward, the final piece here is, and parts of 5.3 actually, predicting whether a reaction occurs in the first place. Now, going on to our ionic equations, right? Everything that is labeled with an AQ, right, we're going to rewrite them, right, in their ionic form, which we showed you guys yesterday, right? So in this formula here, I have 1 barium ion and 2 chloride ions. So we're just going to write it like this. Ba 2 plus 2 Cl minus, right? So what we're doing is we're taking that subscript that was added to the chloride ion and turning it into a coefficient. What this is telling me, whenever something's dissolved into water, right, our ions actually separate from each other. So rather than being 1 barium attracted to 2 chlorides in its solid form, the barium ions and the chloride ions are actually separated by that water molecule. So they're kind of floating around in between water molecules. Maybe the best way to think about that. All right? So that's an aqueous. We have a 1 barium ion with a +2 charge, 2 chloride ions with a -1 charge. That's our ratio, right? Now we'll go to our next one. We have 2 sodium ions. So I'm going to write 2 Na+, and we have the sulfate polyatomic ion, but that 4 right there is a part of the polyatomic ion. Okay, so we are not going to indicate 4 sulfate ions. We're going to leave it written like this, SO4, and we're just going to write 2 minus. We have 1 sulfate ion. So the subscripts that are part of the polyatomic ion, they just stay where they are. We don't turn them into coefficients like the subscripts that we added to it. All right? Now, going over here, we have 1 more aqueous compound, which is sodium chloride, but we put it at 2 in front of that, so we're going to write 2 Na+ and 2 Cl minus. Right? Now, the barium sulfate that we wrote here, which is a solid, we don't write that in ion form because it's not separated. So we're just going to be BaSO4 solid. Okay, now the final phase here, what we're going to do is everything that is aqueous on both sides, right, essentially are what we call those spectator ions. That means they are present and in the mixture with the other ions, but they are not a part of the reaction because they didn't do anything, right? So in the case of chloride, for example, right, we have 2 chloride minuses on this side, right? It looks exactly the same. So the chloride ions remained ions. They did not actually do any of the reacting, all right? So what we're going to do is we're going to go back and cross those off, right? So they are spectator ions. They're not a part of the reaction. Now, likewise, with our sodium ions, right, we have 2Na plus on this side, 2Na plus on this side. So the sodium ions also not a part of that reaction. Okay, so in this case, the actual reaction occurred between barium ions and sulfate ions to form that insoluble compound barium sulfate. So we're just going to rewrite this down here as Ba 2 plus and SO4 2 minus yields BaSO4 solid. And that is our final answer. Okay? So, walking on ahead, let's jump ahead to numero 6, aqueous solutions of potassium nitrate. So we're going to go a little faster on this one. We have K plus, and nitrate is NO3 minus. Ammonium chloride, NH4 plus, Cl minus are mixed. All right? So, they're all ones, which means we don't have to add any additional subscripts. So we're just going to go K, NO3, AQ, plus NH4Cl, AQ, yields. Okay? Now, we're going to go down to our solubility rules, and we're going to check our products. All right? So again, this is a double replacement reaction. So in this case, the ammonium and nitrate are going to swap partners, right? So let's check our ammonium nitrate that will form over here. And it's +1 -1 NO3, so no additional subscripts beyond what's already there, right? Let's check. Nitrates have no exception, always soluble, so this is going to be AQ. All right? Now let's go to potassium chloride, right? Chlorides are usually soluble. Silver, mercury, and lead are the exceptions. Potassium's not, so this one's also AQ. All right? Now, what we learned earlier this week is if all of our products are aqueous, right? That means no reaction. All right? So we're going to stop there. We don't need to proceed because nothing happens in that reaction. Save yourself some time. Check those solubility rules before we go too far. So we don't have to worry about the ions, the total ionic equation or net ionic equation. We're done with that one. All right? So whenever we end up with aqueous, no reaction. All right. Last one that we will do together. Let's go green here. So we got aqueous solutions of sulfuric acid. Now, I made a mistake and I forgot to tell you the formula for sulfuric acid. I should have written that on the board. But that is our formula, H2SO4 for sulfuric acid. We haven't learned acid naming rules, so you guys might not know that one. And then lead acetate, so we have lead 2 plus, and acetate was a C2H3O2, and it's a -1 charge. Acetate's that polyatomic ion. So let's go ahead and write our molecular equation. Sulfuric acid, H2SO4 AQ plus PB. So lead's a +2, acetate's a -2, right? So I'm in fact going to need 2 of those, right? So I'm going to put parentheses C2H3O2 2. and give that its aqueous designation. And let's proceed. All right, so in the case of this one, right, hydrogen is not a true positive ion, but we can treat it as if it were a positive ion. So we're going to swap partners there between the lead and hydrogen. So if lead is a +2, sulfate is, I should write this, +2 minus, 2 plus, 1 minus, right? Okay, so if we form lead sulfate, it's just going to be one of each because lead's a +2, sulfate is a -2. All right, so we need to determine, is lead sulfate aqueous or solid? We'll go down. Sulfates are usually aqueous unless we're with strontium, barium, mercury, or lead. Lead is an exception, which causes lead to be a solid, not an aqueous solution, which goes ahead and tells us that we do in fact have a reaction here, so we'll proceed all the way through, right? Our other compound is going to be H hydrogen and acetate, which actually interesting makes another acid, acetic acid, but let's go ahead and it's a +1 and a -1, so we're just going to go H C2H3O2. All right, now we're slightly out of balance. We need an additional hydrogen on our right side along with an additional acetate, which makes it pretty easy. We'll just throw a 2 in front of that guy to balance it out. All right, we're done. Oh, by the way, acetates are always soluble, no exception. So this is our aqueous one right there. All right, now let's go ahead and write our total ionic equation. We're going to have 2 hydrogens and 1 sulfate and 1 lead and 2 acetates. All right, make sure, by the way, you're indicating the charge on those ions when we separate them out. Everything that's aqueous gets separated into its individual ions, right? We're forming lead sulfate over here, which is a solid, so we don't put any ions there. And then we're going to go 2H plus and 2 acetates. Okay. So we finished writing those in ionic form. We're going to go ahead and identify what remains as ions or in aqueous solutions on both sides. Hydrogen is aqueous on both sides. Cross it off. Sulfate is a part of that reaction. It forms a solid compound, so we keep it. Same with lead. Acetate is in ion form on both sides. So all we're going to do is we're going to take our sulfate ions and our lead ions to yield lead sulfate solid. That is